Here's a surprising fact that most people never hear. According to our best scientific theories, if you zoom out far enough, the universe should look boringly smooth. No special directions, no preferred locations, no giant repeating patterns or cosmic landmarks. Just an even, uniform spread of matter and energy, what physicists sometimes call a cosmic soup. This idea isn't philosophical optimism. It's built directly into the equations that describe the universe. When averaged over vast distances, everything should cancel out. Peaks and valleys should blur together. Order should dissolve into simplicity. But then we actually looked, and what we found was not calm, not uniform, not boring. Instead, the universe is laced with enormous structures, strange asymmetries, unexplained gaps, and behaviors that seem to openly defy expectation. The deeper our telescopes peer into space and back in time, the more uncomfortable the picture becomes. In fact, right now, the universe is behaving so strangely that some scientists are saying something almost unthinkable. Our best theory of the universe may be incomplete, not slightly wrong, not missing a correction factor, not overlooking a minor assumption, but possibly missing something fundamental. And moments like this are rare. These are the moments when science doesn't just adjust, it transforms. For much of the late 20th and early 21st century, cosmology was riding high. We had a model elegant, powerful, and shockingly successful. It was called the Lambda CDM model, and it explained almost everything we could observe. It told a clear, coherent story. The universe began with the Big Bang, a hot, dense origin 13.8 billion years ago. Tiny quantum fluctuations were stretched across space. Gravity amplified those fluctuations, pulling matter together. Dark matter formed invisible scaffolding. Gas fell into those structures, igniting stars. Stars formed galaxies. Galaxies assembled into clusters and vast cosmic filaments. Meanwhile, dark energy, a mysterious repulsive force, slowly accelerated the universe's expansion, ensuring that galaxies would drift farther apart forever. And the stunning part? This model matched observations almost perfectly. The cosmic microwave background, galaxy surveys, large-scale structure, element abundances, everything lined up so well that many cosmologists believed the hard part was over. The universe, it seemed, had given up its secrets. All that remained were refinements, better measurements, more decimal places. But science has a habit of punishing overconfidence. Because the moment our instruments improved, the universe started misbehaving. New telescopes didn't bring clarity. They brought trouble. At first, the problems were easy to dismiss. Small mismatches between theory and observation. Slight statistical anomalies, the kind of discrepancies scientists expect to vanish with more data, but instead of shrinking, they multiplied. Measurements that should have converged began drifting apart. Structures that shouldn't exist kept appearing. Predictions that once seemed rock solid began cracking at the edges. Slowly, an uncomfortable realization took hold. The universe wasn't following the rules we thought it should. And this wasn't the first time science had faced a moment like this. In the early 1800s, astronomers noticed something odd. The planet Uranus wasn't moving exactly as Newton's laws predicted. Its orbit wobbled, subtly but consistently. Rather than throwing out gravity, scientists tried something clever. They assumed there must be something unseen pulling on Uranus. They calculated where that object should be. They aimed their telescopes, and there it was. Neptune was discovered almost exactly where the math said it would be. A triumph. But then came Mercury. Mercury's orbit also refused to behave. Its closest approach to the Sun drifted over time in a way Newtonian gravity couldn't explain. Once again, scientists searched for hidden matter, a hypothetical planet called Vulcan. But Vulcan never appeared. This time, the problem wasn't missing mass, it was missing understanding. Gravity itself had to be rewritten, and that rewrite became Einstein's general relativity, one of the most successful theories ever conceived. So today, we face the same question again. Are today's anomalies a Neptune moment, pointing to something unseen but compatible with our framework? Or a Mercury moment signaling that the framework itself must change? The first major crack comes from sheer scale. The universe forms a vast cosmic web. Galaxies cluster. Clusters connect into filaments, and between them lie immense voids. According to theory, this structure should smooth out beyond a certain size, roughly 1 billion light-years. Beyond that, the universe should look statistically uniform, but reality disagrees. Astronomers keep finding structures that defy this limit. a giant arc of galaxies over 3 billion light-years wide, a cluster of quasars stretching 4 billion light-years, a massive ring of galaxies spanning 5 billion light-years, and the Hercules Corona Borealis Great Wall, stretching an almost absurd 10 billion light-years, 1/10 the size of the observable universe. And then there are the voids, enormous regions with almost no galaxies at all. Some studies even suggest we live inside one, a local hole, roughly 2 billion light-years across. If these structures are real, and evidence suggests they are, then something is deeply wrong. All of modern cosmology rests on one assumption: the cosmological principle. The idea that, on large enough scales, the universe looks the same everywhere. This principle is why we believe our observations matter. It's why studying our corner of the universe tells us anything about the rest. If this assumption fails, we're in trouble, because then understanding the universe would be like trying to judge an entire cake by tasting only the cherry. Those giant structures might not reflect the universe as a whole. They might be cosmic flukes, rare, local accidents that distort our conclusions. And that possibility is terrifying. The next crack hits even closer to home. The universe is expanding. That's not controversial, but how fast? There are two main ways to measure it. One looks at the early universe using the cosmic microwave background. The other measures nearby galaxies and exploding stars, and they don't agree. One method says the universe expands at 67 kilometers per second per megaparsec. The other says 73. That difference is enormous. As measurements improved, the gap didn't shrink, it widened. The odds that this is a statistical fluke are now less than 1 in a million. It's as if the universe is calmly insisting both answers are correct, which means either our measurements are flawed or our theory is. Either way, something fundamental is broken. Then came the James Webb Space Telescope, and almost immediately, it delivered a shock. Webb began detecting large, bright galaxies at times when the universe was only a few 100 million years old. Some date back to just 280 million years after the Big Bang. According to our models, galaxies should grow slowly, small clumps merging over time. Big, mature galaxies weren't supposed to exist yet, but it gets worse. These galaxies contain heavy elements: carbon, oxygen, nitrogen. Those elements require multiple generations of stars to form and explode. Finding them this early is like walking into a kindergarten and discovering fully grown adults. Either galaxies formed at impossible speeds, or the early universe behaved very differently than we thought. And these aren't isolated problems. There are more. The universe produced 3 times more lithium than we observe. Dark matter behaves strangely in galaxy centers. Dark energy may not be constant. It might be evolving over time. If dark energy changes, it would rewrite our understanding of cosmic history and the universe's fate. Even the cosmic microwave background, once considered untouchable, is being re-examined for subtle anomalies. No single issue would cause alarm. Together, they form a crisis. Right now, cosmology is divided. Some scientists believe these cracks will fade with better data. Others think we're standing at the edge of a revolution. But here's the key truth. In science, a crisis doesn't mean failure. It means progress. Science moves in cycles: confidence, anomalies, crisis, revolution. Every great breakthrough came from moments like this. The universe isn't being cruel, it's being honest. The universe is telling us our story is incomplete. Whether the answer is a hidden ingredient, a new particle, a modification of gravity, or a radical new framework altogether. Whether we discover a cosmic Neptune or face a cosmic Mercury, one thing is certain: the universe is about to get far more interesting. And we are lucky enough to be here to watch it unfold. If you enjoyed this journey through a universe on the edge of change, make sure to like the video, subscribe to the channel, and turn on notifications, because the next great cosmic surprise may already be on its way. And when it arrives, you won't want to miss it.